hopefully in the right talk. It's understanding Java garbage collection and what you can do about it, but mostly understanding it. And this is really a simple thing about what the talk is about. This is not a talk about tuning garbage collectors and setting flags that will give you a magic result. It's focused on GC education, on understanding how the actual garbage collection machine works in general, and applying that to the specific environment, JVM, selection of garbage collector you might have, or maybe helping you choose which one you want to use, or which modes. And the idea is that when you understand how the machine itself works and get some of the basic understanding of that, then you can apply thinking as opposed to rote mimicking of flags. You'll learn enough to be dangerous, and most people after they see the stock will go and experiment and play with flags and build little test applications that'll make the garbage collector fall over here or there, and that's a good thing. But it takes a little bit of actual using this stuff afterwards to become truly practical. I've been giving this talk now for about a year. And in fact, the first time I gave this talk was here at SpringOne 2GX exactly a year ago. Well, not here in Chicago. So it's been a very popular talk. I've gotten a lot of feedback that I've incorporated in, but hopefully you'll find it educational. I'm from Azul, and we're very proud of the garbage collection work we do there. We believe we make the best garbage collector in the world, and I promise I won't tell you things about that until the very end. Partly because we're going to spend the first hour of this 90-minute talk defining things, defining words and terms and metrics and explaining mechanisms. And after you have an hour of that, if you're not too tired, you'll be able to much better understand why we have the best garbage collector on Earth. So I have an agenda. But the first hour will be probably a way to pay for the other things I'll tell you later. Let's talk about who I am and where I come from. We'll do that quickly, and then we'll get to the actual material. I'm the CTO of Azul Systems. At Azul Systems, I've been working on all kinds of interesting things, but one of the specific areas I've worked on for a decade now is garbage collection, and a different way of attacking garbage collection, kind of a counter trend to what has been done in the industry for almost 20 years. So kind of a think different approach. This is evidence of me working on garbage collection. This is an actual picture from 2004. We're just perfecting our collector. And that's an actual trash compactor, by the way. And it wasn't compacting very well. I had to get some fragments out the back there. So I took out the book and had a nice photo op. But I other than just making funny photos, I actually work on real things. I've created 2 published algorithms, both the pauseless garbage collection algorithm and the C4 algorithm that followed it, which is a generational form. They're published in peer-reviewed papers. You can find detailed material about them. And beyond garbage collection, I've worked on a lot of other things. I've built operating systems. I've built device drivers. I've built JVMs and runtimes and virtual machines and just compilers. And I've built firewalls and big routers and DSL terminators and Java management systems that ran millions of subscribers for ISPs. So I've spanned pretty much a very wide range of everything from building the kind of applications that probably most of you build to building the infrastructure that those run on, all the way to actual hardware. Garbage collection is certainly a passion within that. Let's talk about Azul a little bit. We have a really simple mission at Azul. We build scalable virtual machines, specifically Java virtual machines. And we do whatever it takes to do that. We've been doing that for about a decade. And when we say whatever it takes, that includes some crazy things sometimes. In our first several years, we built 3 generations, successive generations of custom hardware to solve scalability problems in Java. This is a depiction of a 864 CPU symmetric multiprocessor with 3/4 of a terabyte of RAM that shipped 5 years ago. And it's a beautiful machine. We built this architecture. It's actually our own chips and instruction sets. And we built 3 generations of that. But the reason we built it is we couldn't find hardware to run on that would provide the scalability we wanted. And when we revisited that question every time, we came up again and again with, well, we can't buy the parts, so we have to build them. About 4.5 years ago, the answer came up with, wait a minute, the roadmap from Intel and some degree AMD is looking pretty good. We don't have to design these ourselves anymore, and they're actually starting to look like our architectural picture. And as a result, Vega is not something we design or build new things of anymore. We still sell them to customers that are interested in them. But everything we focus on from both a new product and currently shipping product perspective is pure software for Linux and x86. We call it Zing. It's a JVM for Linux that brings to Linux the kind of advantages we used to need custom hardware for. That's what we build today. That's what we focus on. We're also pretty well known for garbage collection, elastic memory, some virtualization techniques, and visibility techniques. But primarily, we're here on a garbage collection talk. It's what Zing shines on. We power a lot of mission critical things. People run the business kind of workloads on us, and both Vega and Zing are powering a lot of those. And these are just some of the logos of people that would let us put the logos on. A lot of the people that we run things for won't let us put the logos on. Lots of banks, for example, won't, and some interesting government stuff. Okay, so that was background. Here's how we're going to structure the talk. We're going to start with some fundamentals and key mechanisms. I'll introduce some motivation, define mechanisms and terminology. We'll then go on to some metrics and define some metrics and how you should think about them. We will use those mechanisms, terminology, and metrics to classify current collectors you can use in current JVMs. I'll focus primarily on Oracle's hotspot and OpenJDK hotspot, which is pretty much identical. But I'll classify all the mainstream collectors you can get there, and we'll classify them precisely. I'll then talk about a problem I call the application memory wall. And, well, when we get to it, I'll explain what the problem is. And look at our C4 collector in Zing, both from a classification perspective, a little bit about how it works, and why it's there. So that's how we're going to structure the talk. Now before I do that, before I start, I like to do an audience poll. I do this in almost any audience of this size I talk to, and it's a really simple poll. I'm going to ask you how big your heap size is for whatever you run or are involved in or deploy. So how many of you run applications that you have larger than 0.5 gigabyte of heap? That's pretty much everybody, almost everybody, except for people not paying attention, right? Or if you're programming for a phone. So let's up the scales a little bit. More than 1 gigabyte. Okay, more than 2 gigabytes. You can keep your hand up between them. More than 4 gigabytes. Okay, now look around. Still a bunch of people with their hands up, but not quite as many as before, right? More than 10 gigabytes. That's the magic number. We have less than 10. More than 20 gigabytes. We're down to 4. More than 50. Okay, we have 3 people in the audience. We'll talk later. See? No, but there's a purpose to this, and I will get to it a little later. Notice that I guessed pretty correctly where most of you will lie. It's not that everybody's there, but the wide range of people in this audience falls in that range. And the interesting thing is I didn't ask you what your application does. I didn't ask you how big the server you're running on is. I didn't ask you if it's a big app or if it's a data analytics app, if it's a human interaction app, it's a messaging app. All of you seem to be in a pretty interesting narrow band of size. And we will get back to this. Okay. Why should you care about garbage collection? Well, start with what is garbage collection good for? You're all here because you want to understand about it. If you're dealing with Spring, you're probably in a garbage collected environment. But what is garbage collection really good for? It's prevalent. Lots of languages and environments use it. It's very useful for productivity and stability. You've all heard about all the stuff that it really helps with and all the arguments of whether it's really needed there. But empirically, people who build software on garbage collected environments tend to spend more of their time debugging functional issues of their applications and less of the time trying to figure out how they corrupted the heap and caused core dumps. And that's just an empirical thing in long-term maintenance of software, which is why Java and .NET and Ruby and other environments are just more productive. So that's one. There's time to market issues and others. But that's kind of the given. One of the areas I like to focus on is the guaranteed interoperability that garbage collection gives you and how it powers ecosystems and frameworks. Now, when you look at what happens without garbage collection, you're pretty much forced into a memory management contract. If you do anything other than hold things on the stack, which is not very practical if you have half a gigabyte or more memory, then you're going to allocate memory and you're going to somehow have that memory released. And if it's not through implicit automatic memory management with garbage collection, then there's some contract of who allocates and who releases. Does the allocator release? Or if the allocator gives an object to a library, does the library release and the allocator no longer releases? Or do they both release and reference count, and when the reference count goes down to 0, it goes away? And what about cyclical graphs where they point to each other? Who's responsible for breaking those apart? There's some contract that happens every time you allocate an object that has to deal with who's going to free this. And there's nothing wrong with having those contracts, but the contracts have to be consistent. So if you have some framework or library that's written by a single group, a single company, one coherent thinking mode, they'll have a contract, and you can interact with that just fine. And you have another library, and it's got its contract. And you have your code, and you thought there's a better contract. And each one of them can work. But how do you take an object from one library and give it to another library? How do you take an object that came from some sort of a message parsing or format, normalizing thing and give it to your data store, to your cache? How do you go the other way? If each one of them might have a different memory contract. The thing that garbage collection or automatic memory management with implicit releasing of memory gives you is a common contract. The object will go away when nobody needs it anymore. The system will figure it out, and any object can be passed anywhere across frameworks, which is why ecosystems like Java are as big as they are. Because you can take Spring and you can slap it on WebLogic or Tomcat. And nobody has to figure out if they have a matching contract for memory management, for example. Okay, so that's one big one. Another one is that it facilitates the use of large amounts of memory. For whatever reason, I think I know the reason, it's just usually if you have a few gigabytes of memory, they don't come in a two-dimensional array. They're not natural to process in Fortran. So you have data structures, they get complex. As data structures start meshing together, managing them is hard. If anybody here writes compilers, you probably know how hard it is. And the more data you have, the more you tend to have complex structures, and those are facilitated or much more easily handled in garbage collected environments. The last part is concurrent algorithms that are popping up now. There are some concurrent algorithms that are only possible or only practical with automatic memory management, that rely on generation of immutable things that then just disappear when they're not needed, but the actual algorithm doesn't need to track it. So there's some useful things about garbage collection. That's what it's good for. Now, why should you understand how it works? Because this isn't just does it for you. So to explain that, I like to use a real-world story. I call this the story of the good little architect. Anybody here like Mark Twain? So you might recognize the reference. And I like to define a good architect, I think. And the first quality of a good architect is not whether they make the right decisions. It's whether when they make a decision, they can make other people follow the decision. Can they impose their will on a team? Can they make the code in an entire project follow an architecture? Because if they can't do that, it doesn't matter how right they are, they're just a philosopher. So this is the power of architecture, that you can actually make it translate into real-world things. And early in our pauseless garbage collection years, we ran into a good architect. We also ran into an 18-second pause in that good architecture. And that was unheard of for us because we have a pauseless collector. And I'd like to say it's a pauseless collector, but 18 seconds is a little much. So we went in to examine what was going on, and we found out that the application was collecting tens of millions of objects with finalizers on them, actually running finalizers on tens of millions of objects in every little GC cycle it was doing. And those were just super expensive at the time. Finalizers were still a stop-the-world thing for us. We've changed that since then. They're concurrent for us too, but we're trying to figure out what's going on. That's just not a normal behavior. So we examined what the system was doing. We found out that every single class in this project that was written for about 2 years had a finalizer on it. Every class any programmer built for 2 years had a finalizer. That's a good architect. Really strong architect, right? He whipped them all into shape. Now, can anybody here guess what the finalizer was doing? Okay. It wasn't doing nothing. It was doing worse than nothing. It was depositing nulls in every field. Okay. It was doing this thing to help the collector so that objects won't stick around when they're not needed because you need to break chains apart and stuff. And to people who really know garbage collector, that looks funny, but this is not a wrong behavior. It's actually the exactly correct behavior for a C++ system. When you write C++ in complex data structures, you better have destructors, and you better be breaking your things apart and letting them go, and you better have a discipline that goes across the entire project that does that, or you will have memory leaks or worse. But it's exactly the wrong architecture when you have a garbage collector. This is why you need to understand what garbage collectors do and what they don't do, and why trying to help them the wrong way could really hurt them. So we've built some resilience in our collector to this, but virtually all other collectors will show much worse pauses on this specific app. So along with that, there's an intuition thing. Most of what people intuitively seem to know about garbage collectors is wrong. In a crowd this big, there are a lot of misconceptions, and a lot of them are propagated by people, well, propagating the misconceptions. So here's a bunch of things that garbage collection is much better at than you might think. First is that garbage collection is extremely efficient, meaning it is the most efficient way of allocating memory, bar none. There is no more efficient way of allocating and freeing memory than a generational garbage collector in a modern JVM. I'll get into exactly how that works and why I can say that, okay? But its efficiency is actually ultimately tunable. You can decide what percentage of CPU your garbage collector will eat in an application. You can tune it to that level, and all it takes is some empty memory. Dead objects cost absolutely nothing to process. If you make an object and just forget it, really cheap. And when I say very cheap to allocate, modern JVMs allocate an object by bumping a pointer forward. That's all they do, no free list lookups or anything else. Now the other one is garbage collection will find everything that is dead. It will get rid of everything that's not reachable. You don't need to help it. If you're worried about your doubly linked list in a circle having a problem, or some graph that points back to itself having a cyclic structure in it, don't worry about it. All modern garbage collectors will track everything down, will get rid of everything. You don't have to worry about the complexity of your data somehow keeping things alive that the collector won't notice. Now that's not to say that you can't leak, because that's the other side of it. Some things are much worse than you might think. So first, on most modern JVMs, this thing will absolutely stop and stall for about a second per live gigabyte, and you can't get rid of that. You can delay it, you can tune it into the future, but you cannot make it go away. It's built into the system. The other one is that memory leaks are not gone. The memory leaks that are gone are the ones that are a result of accidental, structures that you don't even look at, but they point to themselves. Those will go away. But if you actually still retain or reach an object, it's alive, and it's your job to forget about it. So an entire class of memory leaks is gone, but an entire class of memory leaks remains. And the last one is that It introduces a new performance tuning problem, or a performance tuning counter pattern. Most of the systems I see where people start with a target of running for 20, 30 minutes, passing some SLA, running some number of concurrent users, they'll start off and they'll fail. So they'll tune, and they'll still fail, but it gets a little better to the point where they tune and tune and tune, and it passes. So they're done. They ran for 30 minutes, and it passed the SLA. Most of what happens when they do that is they just took the problem and moved it until it happens at minute 31. And then they declared success. This is a problem that's common in garbage collected environments and rare outside of them. So in garbage collected environments, there are big bad things that happen, and the common tuning technique is to push them into the future, to sweep them under the rug. So you need to be very aware that that's what you're doing when you're tuning, and if you're interested in actually having a system that will run all day, all week, all month, you need to be aware of that. Okay, so I'm going to go quickly through this, but basically trying to solve GC problems in architecture is an interesting challenge. Sometimes you have to do this, sometimes it's unavoidable. If you're building pieces of infrastructure, it's sometimes a good idea. But you have to remember that you may solve your effect on garbage collection with your architecture, but you're living in a very large ecosystem, and your code might be perfect, but is everybody else's? If you're using some library, if you're using Lucene for search, or using Spring, or using a caching engine, or using Tomcat as a container, do you think every code in there is actually following your discipline and your attempt to reduce pressure on a collector or reduce fragmentation in object sizes? It's almost impossible to control. So often it's a waste of time. However, there are many techniques that are applicable, and people do use various forms of object pooling, like database connection pooling, or off-heap storage, which has become popular in the last couple of years, or distributed heaps of various sorts, and external caching. Every one of these has a reason to exist, and every one of them is a good technique in itself when applied in the right places. But in every one of them, you end up building a garbage collector. So unless your problem is really simple and the garbage collector can be done trivially, you're taking, you're moving away from garbage collectors that were developed and perfected over 15 years in the JVM you're running on, and you're building your own. Sometimes it's better, many times it's worse. So an example of trivial garbage collection is caching. A cache is allowed to throw things away. Makes the defragmentation problem really easy. Just throw it away, even if it's alive. But that's applicable only when you're looking at a cache, not when you're looking at a regular object graph. So it's very limited to a scope. Okay, so that was background, motivation. Hopefully you got some. And let's look at some terminology. So we'll start with some more hand raising. How many of you know what a concurrent garbage collector is? Okay, a bunch of you. How many of you know what a parallel garbage collector is? Not as many of you. Okay. I raised those two because they're confusing terms. They are sometimes understood to mean the same thing, so let's define them. A concurrent garbage collector is a collector that runs while your application is running, without stopping your application. So the word concurrent means the collector is concurrent to your application. Okay? A parallel garbage collector is a collector that uses more than one thread to do garbage collection. It's parallel with itself, right, within itself. You could be concurrent but not parallel. You could be parallel but not concurrent. You could be both. You could be neither. They're orthogonal terms. Now, the reason this is confusing, and the reason lots of times people kind of go, oh, I think I know what concurrent is, but wait, what is this parallel thing? Part is just language. The words are synonymous to a degree. When you translate them, they become really synonymous. But also, if you look 30 years back at academic work on garbage collection, what we today call concurrent is called parallel in some 30-year-old papers. So this is a global problem. Anyway, this is what people mean today and for the last 10 or 15 years in academic work. So that's the clear definition, and it's a very important thing because it's a huge effect on behavior. So as long as we're defining terms, let's define a few more. You guys have heard about stop the world. You've probably experienced what stop the world is. Stop the world is the opposite of concurrent. You're either concurrent or you stop the world. Now this is not a global statement about the entire collector, but at least one part of what you do is one or the other. Another word is incremental. Incremental usually applies to stop the world, because in concurrent you don't really care. And when you have a stop the world operation that's this big, sometimes you have to do it in one shot. We call that monolithic. I don't have that up on the slide. So it's all or nothing. You can't do half of it and let the program run. So for example, if I've moved an object from point A to point B, I can't let the program run unless I make sure the program doesn't follow a wrong pointer. And there's a lot of pointers to fix. That would be an example of monolithic. Incremental is when you could take a big problem like that and you can chunk it into pieces and you could say, I'll do this much, and at the end of the increment I can let the program run. So I'll stop the world, I'll do a little bit, I get to a place where it's safe to allow the program to run, I'll let it run a little bit, then I'll stop it again. It's the same amount of work, but spread over time. Or sometimes you have a trade-off where you're willing to do more work, but you'll do it incrementally with smaller pauses. Now the last word I like to define is really simple. It's the word mostly. And it means exactly what the English word means. It means sometimes, right? It also means sometimes not. And what's important to understand is whenever you see the word mostly attributed to garbage collection, you have to read it the opposite of what the rest of the sentence says. Mostly concurrent means sometimes stop the world. Mostly incremental means sometimes monolithic. Mostly parallel means sometimes it's not. Otherwise it wouldn't have the word mostly in front of it. Okay? So it's telling you that right there. Okay, now we get to some other definitions. Precise versus conservative collection. Anybody here know what a precise collector is? Okay, good. So now you learn stuff. So a conservative collector is a collector that's not quite aware of where all the pointers are. In fact, most historic languages are conservative. And in most languages they're not absolutely type safe and don't have a lot of information coming about where everything is. You don't quite know if something's a pointer or an integer. And when you don't quite know if something is a pointer or an integer, you have to be conservative in treatment. So there are two things you do that's conservative. One of them is, well, I don't know which it is, so I'll assume it's a pointer and say whatever's there, that's alive. But it also means I can't move an object from point A to point B, because if I look at an integer that happens to have a value equal to its address, I really don't want to change an integer the wrong way. So it highly limits what the collector can do, but it is common in a lot of systems. And then a collector is precise if it is the opposite. It knows where every single reference, every single object pointer is at all times, or at any time where the collector needs to run. Okay? So it actually has this global knowledge, and it's able to track them all down, figure out stuff with all of them, and change any of them that it wants because it knows where they all are. It's necessary to be precise in order to move objects. Otherwise, we just talked about the problem. But the other thing is that the work to be precise is actually not really the garbage collector doing work. The garbage collector has it easy. Somebody else has to tell us where all the pointers are. That somebody else is usually the compilers. The heap itself is fairly simple. Heaps tend to be self-describing. Objects have types that you can derive at runtime. But the stack, the code, has things in registers, things on the stacks, things in temporary variables. And if you're garbage collecting at a certain point in code, you need to know where all those are and which ones need to be followed or changed. That means the compiler has to sprinkle all this information that's there for no other reason at very, very high resolution in the code. JIT compilers do that on all JVMs today. In fact, all commercial JVMs today are precise. There are no conservative JVMs that you have to deal with. But this quality sets JVM and, say, .NET apart from a lot of other runtimes. And the real issue with conservative collectors is that in most environments in modern world where you have variable object sizes and you want to run for a long time, a conservative collector will almost always run into fragmentation, which will require a restart because it can't move things. So every single commercial JVM has a moving collector. They will all move objects at some point in life. Okay, we talked about preciseness. Well, how do we do this precise stuff? Well, the collector uses something called a safe point. And a garbage collection safe point is a point in the execution of a thread, or a range in execution of a thread, where there is full knowledge of all the references for that thread are in the stack, in the code, in registers, maybe two registers that together are a pointer. All kinds of things like that could happen. But it's a point where we know everything. It's well described. And between those points, it's not necessarily well described. That means we can't do garbage collection operations between those points. A GC safe point is that. Now, I often will say safe point as opposed to just GC safe point. They're kind of interchangeable, but there are other types of safe points in the world. For example, the optimization safe points, where the compiler wants to take optimized code and revert it to less optimized code and to interpreted stuff. Then it needs information not just about references. It needs to know where every variable is, even if it's not a reference. So a GC safe point is a subset of the safe point capability of a JVM. When we say bringing a thread to a safe point, or to bring a thread to a safe point, it's to get the thread to execute to the safe point and not past it. I'm picking my words carefully because bringing a thread to a safe point doesn't mean stop it at a safe point. Sometimes it means that. It means don't execute past the point where I know where all the references are. Here's a classic example of when that happens. Every time you make a JNI call, a native call into non-Java code that you write or that is part of the runtime, you cross a boundary that makes this a safe point. Within that code, no changes to Java references can happen. If you do access a Java reference, you're crossing back across the safe point to code that is not in the C side but on the runtime side. Which means that you could be at a safe point for an hour, spinning CPU and inverting a matrix in C++. Being at a safe point doesn't mean stopped. You did not give up the CPU necessarily in doing it. Okay? What you can't do is get back to code that manipulates or looks at references before you, without crossing the safe point again. When we talk about a global safe point, I forgot to say, safe point opportunities really need to be frequent. In general, we have them in method calls and back edges of loops, so they're pretty frequent. But if a compiler accidentally makes safe points go away for a few seconds, that's a big problem. Because we have this concept of a global safe point. A global safe point is, let's get all the threads to a safe point so we could do something globally. And that is usually the stop the world pause that you experience. It's a global safe point. All threads are stopped at a known, well-defined, described state, and the garbage collector is doing stuff. The problem with infrequent safe points is that if you have 100 threads and one of them is running a 5-second loop before it reaches a safe point, the other 99 are at a safe point waiting for it to get to its safe point, but no work is being done and the collector can't do anything yet. So that's why safe points need to be very frequent, as in microsecond frequent. So we describe precise collectors. We describe what safe points are, which are necessary for precise collectors. And let's talk about precise mechanisms, what they all do. So every single collector that's precise does all three of these things. It will identify the live stuff, it will track down the dead stuff and find a way to recycle it, and it will move objects from point A to point B, at least in some. Every single collector out there does all three. Yeah?
A question about safe point. Let's
Yeah.
say I make an IO operation where I need to go either to a database or to a file. Is that considered a safe point, or is that window not safe?
So all blocking operations in all JVMs that are, worth using, which is most JVMs are pretty well done there, will be at a safe point. That's a very good example. Your system calls, your blocking operations are virtually always at a safe point. You don't want long-running non-safe point operations, which is why anything that's indeterminate in length should be a safe point. Now, it's not your job to introduce them. You don't have to worry too much about them, but you should understand what happens if you allow a compiler optimization that takes Safepoints out of loops, for example. And somebody shows you how the code really runs a little like 7% faster because of that. Well, yeah, but it comes with an indefinite pause. So that's not a garbage collection pause, by the way. If you look at the garbage collection logs, they do not report that time as a pause. They count from the time they got to Safepoint and the work they did. In fact, you didn't get at a Safepoint. That's not the garbage collector's problem. It's not its fault. Right? By the way, if you in Hotspot, if you do print application stop time as opposed to just verbose GC, print application stop time will report the inclusive time that includes the time to Safepoint. And sometimes you'll see seconds of difference between those two. So all collectors will, all precise collectors do all three of these. And let's look at examples. Mark, sweep, compact is a common collection technique used for all generation collectors. Mark, sweep, compact is every one of those steps. The first one is mark, the second one is sweep, the third one is compact. But another form of doing all three is a copying collector. You take all the objects from a from space and you copy them all to a to space, and now you have an empty from space. That's a single pass that does all three of these things, not three different steps. But all three things will occur in every precise collector you can get your hands on. So let's look at those parts. What is marking? Marking is the good magic thing that lets us know where the live stuff is and where the dead stuff is and where you don't need to worry about cyclical things. It's very simple. It's exhaustive but simple. It starts from what we call roots. Roots are static variables in threads, although you could say the threads are not roots because the static variables point to them, or to a list of them. But you start from roots, places where you know where to start and there are references there. And you find all the references there, all the stuff on the stack that the Safepoint tells you are references and all the static variables. And for every reference you run into, you follow the reference and you mark that what you're following is alive. Then you look inside and you follow all the references in that and you mark them as alive. You basically paint anything you can reach. And you do that exhaustively. When you reach something that is already marked alive, you don't need to look into it because it's already been dealt with. And eventually, you will paint everything you can reach. I should have said that along with this. And at the end of a mark pass, basically everything that's reachable will be marked live, and everything that's not reachable is not reachable and cannot become reachable in the future. So it's dead. You can recycle it. If I can't reach it from the roots, there's no way for me to somehow reach it later. There's no way to propagate that state around. That's what marking and garbage collection basically relies on. Complexity is very important here. Marking is linear to the live set, to the number of objects, size of objects, number of references that you have, not to the size of your heap. If you grow the heap, but don't grow your application use of the heap, you don't change the amount of work done by marking. You can make the heap 10 times larger. It doesn't change marking at all. You change the live set, grow and shrink that changes the amount of work marking does. Okay? We'll touch on that in every mechanism. Sweeping, that's very simple too. So we marked and we scan the entire heap, and if it's alive, well, it's alive, and if it's dead, we need to somehow recycle it, so we probably are going to put it on some sort of free list. There are many techniques for doing that, but basically we take the dead things we run into and we put them on a free list so we can later allocate into those holes. Think of malloc, but with automatic free scanning. Very simple, not much to talk about. Complexity, this is linear to the heap size. You grow the heap without changing your application, you grow the complexity and the amount of work sweepers do. So that part is linear to the heap, not to the live set. Compaction, well, first of all, why is it needed? Why is it everywhere? Why does every JVM have a compactor? And why does every collector run a compactor without avoiding it? At least not very long. Over time, you'll have variable size objects, and the heap will get these Swiss cheese holes in it. And objects come and objects go. And at some point, you'll get to this point where half your heap, or 90% of the heap, is empty, but it's on these holes, and you want a 10 kilobyte array, and there's no hole big enough for that. And what do you do then? well, half the memory or 90% is empty, it wouldn't be very good to crash. And this is the thing a conservative collector faces, because when it reaches that extent, nothing it can do. What you do is you just move objects together to make larger contiguous empty space available. That's what compaction is for. It's a defragmentation operation. Compaction is made out of two key parts. One of them is the moving of objects, right? Relocating the objects to new places. The other one is fixing all the pointers to the objects, the remapping of pointers to point to the correct place. So relocate and remap are the two parts of compaction. Yeah. Not every GC cycle, but every garbage collector compacts. Every one of them has code that compacts, and we'll get into the mechanisms and when they do it and when they try to delay it, but every one of them does it quite often. And no. That's why compaction is there. If it didn't compact, it would have to throw out of memory at that point, which would not be a good thing. But this is why every commercial JVM compacts, because it wouldn't be acceptable to do anything else. So the hard thing here is actually the remap. You move one object, there may be 3 billion things pointing to it, and you need to make sure you got them all right before you are done. So moving an object is very expensive, not because of moving the object, but because of remap. That's why we tend to move a lot of objects at the same time, because we can amortize the scanning for remaps across all the objects we moved. It would be extremely inefficient to move one object at a time, because each object we need to scan the entire life set. Complexity-wise, compaction, as complex as it is still just linear to the life set. You just have to move the life set, and you have to scan the life set for references. So growing the heap does not make compaction more complex or more work. Okay, we covered mark and sweep and compact. Let's talk about copy. It's a different technique. Copy, as I said before, starts with all the objects being in a from space, and it basically moves them all to a to space. And at the beginning, everything is in the from space, everything points to the from space. We basically start with the roots, and anything we reach, we copy over, and then anything it can reach, we copy over, and by the time we're done and we exhausted everything, this is not a mark, it's a copy. When we're done touching all the reachable objects, they've all moved to the 2. So at the end, everything is in the 2 space. Nothing left in the from space. And all the references are to the 2 space, and we're done. It's a single pass operation. Its complexity is linear to the life set. Okay? So we talked about some basic mechanisms. Let's compare them a little bit, or examine how, they relate to each other. So copy is really cool, but it has this problem. You start from the from space and you move everything to the to space, and it's usually monolithic. You start and you can't stop. So you need a to space as big as the from space if you're going to do this safely, because you don't know that anything's dead. Maybe just 2% died. So you need a lot. So you theoretically need twice as much memory. You need an empty place that's as big as what you've filled up, not knowing how much is dead or not before you do this. And if you don't, you may not be able to finish and revert. There was a question?
Do you need to do a remap in this case?
No, the copy is a single pass that effectively includes the remap. So every object you visit, you copy, and then you look at all its references and you copy the things they point to, and you fix the references as you do this. So you never have, it's a single pass. Okay? It's efficient that way. So copy requires twice the memory on its own. A mark compact alone, without a sweeper, so this is you mark and then you compact by moving elsewhere to a 2 space, but only on parts. That one requires 2x the memory, but only if you want to do the entire thing in one pass. Mark compacts don't have to be monolithic typically. So if you just don't have enough memory, you could just stop and do that in the next cycle. It's a little more robust that way, but that's not a strong and necessary thing. There are other tricks around that. Mark sweep compact doesn't have this problem. Mark sweep compact compacts in place. You do the whole mark, and then you have all these holes, and then you shuffle everything to one side. You're going to go and you squeeze everything in place. You don't need a two space because you know where the holes are, and every hole you just squeeze. Right? So you get to a hole, you move things to cover the hole. That works well. You don't need 2x the memory, so it's less memory. Complexity-wise, though, copy and mark compact are linear only to the live set, while mark sweep compact is linear to the heap size, at least in big part. So that's the complexity part there, and you'll see in a minute why that's very important. And mark sweep and sometimes compact is a common technique for trying to deal with the cost of compaction. Copying, I already said, is typically monolithic. So these are qualities of these different mechanisms. Hopefully you're learning things here. When you hear copy or mark or compact or sweep now, you know more about it. Generational collection. So this is a very cool technique. It's surprisingly young. It's, I think, less than 30 years old. And it's based on something called a weak generational hypothesis, an observation that most objects and most programs die young. It is such a powerful observation and so global that every system that you know of that runs on servers at least will use it. How does this work? Knowing that most things die young, we try and make garbage collection more efficient. And we make it more efficient by saying, if we could focus only on the young parts, and we know that most of them are dead, and we use an algorithm whose complexity is linear to the live set, not the heap size, knowing that most of the heap is empty and the live set is a tiny percentage of the heap, then we will get extreme efficiency. As long as we could keep the live set to be a tiny fraction of the heap being collected, we've got a huge, then a copying collector is dramatically more efficient, as in 50 times more efficient than a mark sweep compact for that heap, as long as that quality exists. So how do we do that? Well, we keep this notion of a young or younger generation, and we maintain that quality of sparseness in it. So it naturally, the things that were recently allocated will naturally be sparse, because most of them will die quickly by the time we're doing the collection. But some of them will live for a while. Some of them do live. In fact, most live objects are live for a long time. It's just that most dynamically allocated objects expire very quickly. So most of the stuff that actually lives long. So we have to get rid of the long-lived stuff. We have to promote it somewhere else, move it out of that part of the heap that we focus on, because if we didn't move it, we would lose the basic assumption that that part is sparse. If they stick around, they make it non-sparse. They grow and grow and grow. Now we have half of it's alive. We no longer have efficiency. So we collect the older generations only when they fill up. And that happens a lot more slowly because the young generation is really a very good filter. Now this technique is extremely efficient and it's almost globally applicable. There are very few applications that don't benefit from this. The exception to this rule is things like initial load time or initial hydration time of data in memory. When you're actually loading from disk and putting in memory, almost everything you load sticks around. And at that point, the efficiency isn't that great for that part. But if it's just the load time, afterwards everything becomes good. So this is a great way to keep up with allocation rate. It's so great that it's not practical to run on a modern server and keep up with this allocation rate CPUs actually want to do without a generational collector. That's why every commercial JVM you could get your hands on does a generational collector. So that's the technique itself. How does it work? Well, I explained what it does, but how do you focus just on part of the heap without the whole heap? I explained root marking and reaching. So in order to say I'll only look at one part of the heap, I need additional roots. I need to know about everything that is outside of that part of the heap that points into it. And I need to treat that as roots. And then everything else is the algorithms we talked about before. So we call that a remembered set. Remembering the set of things that point into a region, the young generation in this case. And a remembered set is basically a set of roots, additional roots, in addition to statics and threads that are considered that. Every pointer from the old generation to the young generation is in a remembered set. Has to be, or we won't have correctness. The cool thing about generation collection is that if you use a copying collector, which is super efficient live set only, single pass, for the young generation, and the young generation is a small part of overall heap, you don't need twice the memory for the copying collector. You can make optimistic assumptions that very little will survive. The survivor spaces could be much smaller than the Eden space, for example, in collectors that either make you or allow you to set that. But if you got it wrong, you just spill over to the old generation. So you can continue working, even though you're monolithic. So the 2x overhead part goes away if you use it only for the young generation. And usually, I told you I won't tell you too much about tuning and flags, but this is a relationship you really want to keep. You want to make sure that things stick around long enough, but not too long in the young generation. And this is not a hard thing to do. So if you don't want things to be promoted immediately if the young generation finds them alive, because when you decide to collect, there's a whole bunch of objects that were just now allocated, and they're about to die like this. But you were unlucky enough that they happen here. In fact, in many places, most of the objects that would be found alive at the collection time are actually about to die very quickly. So by allowing them to stick around at least once in the young generation, before you promote them, you gain efficiency and you kill a lot more things in the young generation. You get a much more effective filter. So you really want them to stick around more than one cycle in the young gen. But if you stick around too long, the whole young assumption will die and we'll lose all the efficiency. So you don't want the young generation to be too small. You don't want the retention policy, the promotion thresholds, depending on what lets you set them, to be too low. A 0 is not good. But if you set them too high, you basically have a non-generational collector. So, and a copying one at that. Okay. So how does this remembered set work? We talked about, yeah, go ahead.
It seems like you keep bringing up other ways that the garbage collector keeps track of information. So maybe you'll talk about this later, but it seems like the garbage collector itself will start having a lot of memory that it needs to keep track of things. Does that ever become
So far, the remembered set is the only thing I've introduced that the garbage collector needs memory for.
And also the set.
The thing in the Safepoints?
Yes.
That's not the collector.
Oh.
It's compiled code. It comes with compiled code. It's annotation of compiled code.
And keeping track of how many generations each object has been around for also takes care of that.
That's a good point. So there are little things like how long have I lived, how many cycles have I lived, bits that it could sprinkle in places. Usually they sprinkle them in the objects or in object headers. But yeah, the collector can add all kinds of metadata to things. Usually they're very cheap as percentage of things. The remembered set is an interesting one because for efficiency, typically you sacrifice some percentage of a heap size for it. And how does this thing actually work? We need the remembered set. We explained that. And the way it's usually done is every store of a reference into the heap needs to track something. And card marking is a common technique that's used for that. So the way card marking works is we have this card table where a 1 in it says there's a suspect reference there you should treat as a root potentially. And every time you write to an address, you also dirty the card that it's associated with. It's a very simple technique because you just take the address, you shift it, you get the card address, you set a 1 in it. In fact, Hotspot in its common path does what's called a blind card mark. It doesn't even check to see if this is across generations. It just stores a 1 somewhere. And the reason it does that is because processors are really good at storing things without checking. Goes through the pipe, no code depends on whether the store happened already or not, so it's very efficient. There are other techniques like precise card marking from a resolution perspective and exact card marking from a conditional card marking that checks and only only marks as needed. Excuse me for a sec. Okay. Hopefully this fixes itself. That was a short pause. So card marking is usually a side structure. It's either an array of bits or bytes. And in hotspot specifically, there's a byte for every 512 bytes of the heap. When you find a dirty card, you know that in associated addresses, there may be a reference that you need to look into the young generation. It may have been overwritten. So it's suspect, but you go look in it. Usually these are fairly sparse and you can clean them up because the generational assumption wouldn't work if they weren't sparse. So we put a lot of different things together. Let's look at how they come together in most commercial JVMs. The young generation is usually a copying collector. It's usually monolithic and stop the world. At this point, you should know what all those mean. The old generation is usually some form of mark sweep compact or mark compact. It could be any of these. It could be stop the world or concurrent or mostly concurrent or mostly incremental or incremental, and anyone. A lot of variations out there. Here's a bunch of terms, and I'm not going to get into each of them. The mutator, by the way, is what we call you guys. You're mutating the shape of the heap as far as the collector is concerned. But monolithic stop the world is basically the big bad thing that you see as a pause. On metrics, interesting metrics like allocation rate, mutation rate are important to understand, partly because they scale with your application. I don't need to know what your allocation rate to know that it will double if you double your transaction rate. I don't need to know what your mutation rate to know that it'll double along with it. They're a result of work. And allocation rate is intuitive. Mutation rate is how fast do you modify pointers in the heap. And that will double if you double your speed or what you do. This becomes interesting when your collector is sensitive to them, where too much is too much. Marking time, compaction time, I think they're intuitive. We won't get into these here, but if you want to later look at what's written there on the slides, you're welcome to it. Let's look at a little bit of interplay here. We talked about mechanisms. Remember I said how garbage collection is ultra efficient, nothing is more efficient than that. How does that work, and how can we make such a broad statement? So here's a picture. And this is really heap size on x-axis and CPU efficiency, or CPU percent on the top. Let's draw the live set of an application here. Now, if you have less heap than the live set, this is not a working system. Okay? If you have exactly as much heap as the live set, like 1 byte empty, it doesn't matter what garbage collection algorithm you're using, you're thrashing and you're spending all your time on garbage collection. I have 1 empty byte in a gigabyte. When you allocate it, you freed 1. But when you want that 1, I need to go find it in a gigabyte. And it doesn't matter what algorithm I use for that. I've got no idea where you freed it. I'm going to scan a gigabyte in some way to give you 1 byte. That's not efficient. Okay? So that's the 100% CPU point at exactly that point. Now the other intuitive point is actually over here. Well, over there. If I have infinite memory, I never have to garbage collect. That's 0% CPU. There's an almost perfect line that connects those. It's 1 over x. Every time you double the empty memory, you double the efficiency of the collector. If you had 2 bytes instead of 1, it'd still be very inefficient, but half as inefficient as before, right? And that is very powerful as you start growing that number. So if you have a garbage collector that's taking 50% of the CPU, you want that to be 25%, double the empty heap. You want it to be 5%, give it 10 times the empty heap. Notice not the heap size, the empty heap. So grow the heap size so that the difference between live set and the heap size grows, your efficiency goes linearly with that. That's true for almost all collectors, and you know, here's wording that explains that. I just talked to verbiage, but if you read the slides later, that says the same thing. Sometimes the picture doesn't explain itself. What does empty memory actually do? It lets us exchange CPU power and a very powerful exponential growth. The amount of memory, empty memory, is really a dominant factor on the amount of work done. Okay, Both copy and mark compact are perfectly linear to the heap, to the live set, so the amount of work they do is fixed for the live set. Doesn't matter what the heap size is. How often you need to do them depends on how much empty memory there is, because as you allocate, when you run out, I have to do it. So basically the collector has to perform a GC cycle every time you run out of empty memory, and that determines how often it does a fixed amount of work. So make it happen less often, you've got a more efficient collector. So basically it's got a perfect doubling. Since most commercial JVMs use a copying collector for the young generation, and that dominates the allocation and dominates the collection, the actual collection of data, that behavior works almost perfectly for all of them. Okay, so that's what controls efficiency. But what does it not control? It doesn't control stop the world behavior. It controls how often you have to do them, but it doesn't control how big they are. They will stay either the same or get worse as you grow the heap. So for copy and for mark compact, they'll stay the same. Mostly the same. Remember mostly? But mark sweep compact is also linear to the heap size, so the pause will actually grow. It will still become more efficient because the mark and compact parts become more efficient, but the sweep doesn't. Okay? So great way to reduce CPU consumption, useless for controlling worst case behavior or pause time. Okay? So pause time. Pause time is a problem for a lot of people. What can we do about it? So here's some non-monolithic stop-the-world stuff that people do. There are tricks and algorithms and things you should know about. I'll touch on a couple and then we'll move on to classification. Concurrent marking. We talked about how you mark things. That's very easy if nothing moves, nothing changes. But there's a classic problem when the heap is mutating, when the references are changing while we're doing this. And the classic concurrent marking race goes something like this. The collector is marking along, painting everything it can reach. Your program takes a reference that the collector's never seen before, because it hasn't reached it, copies it to a place the collector's already visited, and then erases it over there. If the collector proceeds and marks everything and thinks it's done, you're going to have a live object the collector didn't see. And that's a really bad thing because it's going to recycle it and you're not going to be happy. So that has to be closed. Any concurrent marker has to somehow fight this, combat it, make sure the marking is correct even with that behavior. A common example technique is to use multipass marking and mutation tracking. The way this works is as the collector is marking along, when you write anything to memory, that's tracked. And when the collector finishes a pass, it goes and looks at all the stuff you wrote while it was doing this concurrent operation, and it marks all that. But when it's doing that, you're doing more changes, right? So when it finishes that pass, it goes back and does that again. And at some point, the list will be short, or it'll think it's done, or some collectors just say, I'll do one pass and then I'll stop. It varies. But at some point, you do a little catch-up stop, and you hope that's short. That technique works pretty well, but it's sensitive to a very important metric, mutation rate, which basically means your throughput. The amount of work that it's accumulating while it's doing its constant job is growing if you grow your throughput. And at some point, it will either never finish the cycle, or it can finish it, but it takes so long it doesn't matter. You've run out of empty memory and you're waiting for that, right? So collectors that do multipass marking are, if you test them at one throughput, that doesn't mean you've seen the pause times because, as the throughput grows, they may just fall off a cliff and have to revert to a different algorithm, okay? But it is a commonly used technique. It's a good technique. You just need to know its limitations, okay? Multipass marking. A different way to look at avoiding monolithic stop-the-world is not how do we concurrent, but how do we break the stop-the-world into pieces. That's incremental. And incremental compaction is something you probably heard of with the G1, garbage first collector, or with the balance collector from IBM. JRocket had done it as well before that. And the way incremental compaction works is that you have additional remembered sets. In addition to remembering what points to the young generation, you actually start tracking regions, and you say what regions point to what regions, or what reference objects point to what regions. And you have a lot more remembered set data. And what you do is you basically look to compact a single region, you only need to remap the references in the regions that point to it, which is not the whole heap. So you could compact an object or a region and not pay the entire heap remap. So what you then look for is sets of regions that together have sets of regions that point to them that are small. So if I have one region and 1,000 regions in the heap, but only 93 point to this one, and I have another region that only 57 point to that one, but they're not unique, 93 and 57, they overlap mostly, so I could take these two regions and pay only 103 regions. Something of that kind of math. You look for sets, the collector looks for sets that it can do the relocate work and the remap work on within a contained pause or a target pause. If it can find a set like that, it'll do that. If it can't, it'll do the next best thing it can do, right? The smallest set it can find. And if absolutely can, it'll do something else. But that works, and it works pretty well, but it has a couple of sensitivities. The first one is popular objects. So that for one object in a region to be pointed from most of the heap for you to avoid compacting that region, but eventually all regions will have one popular object in them and you're going to need to deal with it. The other one is that the complexity of this algorithm grows to the square of the heap. Remember all these other complexities we talked about? This is an n-square problem. The number of regions grows to the square of the heap, and the number of regions that point to any one region the number of regions grows linearly with the heap, and the number of regions that point to one region grows linearly with the heap. That's an n-square problem. So it's got some issues, but mid-size heaps, it has, and for certain behaviors of objects, it could work well. In general, if you look at how people evolved algorithms and tuned collectors over the past 20 years or so, I call that a delaying the inevitable tactic. And collectors have gotten much better over that time. And what I mean by delaying the inevitable, we pick the hard thing that we want to avoid, and we can't eliminate it, so we make it happen more rarely. So compaction tends to be one of those things. For example, generational collector is a great delay tactic. We end up with old generation happening less often. The young generation pauses tend to be small. So we've pushed a big pause into the future and made it more rare. That's a good thing. It's not elimination, it's delay. And eventually we have to deal with the old generation. So in the old generation, we have techniques that say, well, can we collect and recycle in place without compaction? That's mark sweep and sometimes compact. And techniques like CMS will do that. But eventually we'll get fragmentation and we're going to have to compact. So then we have incremental compaction. If we have to compact, can we do that in small parts? And that works okay as well, but eventually you'll have popular objects or complexity issues and you're going to have to deal with those too. Each one of these is an improvement. But that's an improvement of sweeping things under the rug. And eventually you have to deal with the fact that there's a pile of dust under there. So let's classify some collectors. At this point, this should be good terminology that all of you now understand. So let's go through them. I said already that this is the typical combination in commercial collectors. Let's look at them specifically. The most popular collector used in Java anywhere is the parallel GC collector. It's a really simple reason it's the most popular one. That's the default collectors that you get if you say nothing. So that's why it's popular. Here's how it classifies. It's got a monolithic stop the world new gen. It's parallel, but it's monolithic stop the world. And it's got a monolithic stop the world mark sweep compact old generation. Okay. Now every single word here is now defined. Hopefully that worked. Okay, let's move on to the next one. The concurrent mark sweep GC, also known as CMS, but that's the actual flag you use. It's use conc mark sweep GC in Hotspot, is a mostly concurrent collector. That's how it's classified or how it's said. What does that mean? Remember mostly? So what do you think the classification of the new generation on this collector is? It's a pure monolithic, stop the world, copying new generation. The word concurrent doesn't appear here. Concurrent only relates to the old generation in this collector. Okay? The old generation is a mostly concurrent collector in itself. It's got a mostly concurrent, non-compacting old generation. The marker is mostly concurrent. It uses that multi-pass technique I described, and it actually does a very nice and efficient trick. It uses the fact that the generational collector already dirties cards for its barriers every time you write, and that means any mutation of references dirties a card somewhere, so it uses the card table as the indication of tracking of stuff, so it just scans the card table and cleans it, which is a cool trick. No additional memory needed. But it has the multi-pass behavior with the multi-pass sensitivity to throughput. Okay? It's got a concurrent sweeper, and concurrent sweeping is not it's fully concurrent. You don't need stop the world for that. But it doesn't compact. So what does that mean? When you see mostly, there's usually that. There's a fallback to a full stop the world monolithic old gen collector. Okay? That when you see a promotion failure message in your log files or a concurrent mode failure in your log files, it's either that it has to compact or it can't keep up, or one of those. Okay? Yeah.
I heard your new gen and your old gen. I figured that to be more historical, like the earlier collectors would be the old gen, the new ones would be the later ones that come out with newer algorithms. Is that just history, or is it also configurable options in these variables?
So to be clear of what I mean by new gen and old gen, new gen is the young generation in a generational collector, and old gen is the old generation. We apply different algorithms to different parts of the heap usually because of their efficiency and choices. But this is it's not new or old from an age of an algorithm perspective. This is just from an age of object perspective. Okay? New gen here means the new gen and young gen are synonymous. Forgive me if I flip them around. Inside the actual source code for hotspot, we call it new gen, and your flags we call it new gen. That's why I put it up here. In academic work, usually you call it young generation. Okay, so that's the concurrent mark sweep collector, G1, GC, or garbage first. A mostly incremental, I don't know if I'd call it mostly concurrent, it's somewhat concurrent collector. It's got a monolithic stop the world new gen collector. Okay, no surprise there. Has a mostly concurrent old gen marker. It's got a slightly different technique than CMS, but I'm not going to get into the differences here. Similar sensitivity, similar multi-pass behavior. But it has a stop the world mostly incremental compacting old gen instead of trying to be concurrent there. And its stated objective is avoid as much as possible having a full GC. What does that mean? That it has a full GC. Okay, remember how to read these things. Okay, and it falls back to a full GC when popular objects or other falling back behind issues come up. When the complexity hits it so hard, it'll do a. So application memory wall. At this point, I've given you a lot of terminology, some understanding of how garbage collection mechanisms work, and I'm going to come back to this slide. Remember this from the beginning? So why is this a problem? Why am I noting that you are all in this narrow range, and why am I saying that's a narrow range? Because that's a lot of memory, right? Well, here's what servers cost to as of yesterday on the Dell site at retail levels with no discount. That's what servers are today. The smallest server on this list that costs $5,000 has 128 gigabytes in it. There were 3 people in this audience that use half of that server. Most of you don't use anywhere close to that. And that's the smallest server on the list. And why is that a problem? Well, I mean, we could look at it in many different ways, but I actually tend to think it's an industry problem. We want people to keep building bigger and bigger and cheaper servers. That means we want applications to want larger servers, or people won't build them. If an application couldn't care less whether a server has 32 gigabytes or 320 gigabytes in it. At some point, people won't manufacture the stuff people don't care about or buy. So today's servers are extremely cheap on memory. Memory is so cheap you should consider it when you're thinking about wasting your time to save it. It's less than $1 per gigabyte per month. It's a lot less than your salary. And we have tremendous amount of memory bandwidth in these servers as well. So that's today's server. That's what a server is today. Servers are not these little toys you might have thought of 10 or 15 years ago. So, you know, a common thing is, okay, but do we really need that much memory? I mean, what kind of applications need that amount of memory, right? So the application memory wall is a very simple observation. Our applications, for some reason, empirically, just don't grow to use current server sizes very well, and that problem is growing roughly at Moore's law rates. So it's a pretty big problem, growing really fast. So to this thing of how much memory do we really need, you know, I get this question a lot, and all I do is I just point back to history and say, you know, asked and answered. This is probably a common example of asked and answered for that specific question. He made a lot of money after that. So, but I think we probably agree none of us programmed to 640K, right? So what is the right size? Is it one of these? Because right now the audience is somewhere between these two numbers. Okay? Meaning somewhere between 1,000 times that wrong thing and 10,000 times that wrong thing. So anybody want to bet about the right thing? And by the way, to be fair to Bill Gates, he said he didn't say that. Okay, he said something else, and anybody that would say that doesn't really understand computers. But the reality is we have a moving target. It moves at roughly 50 to 100x a decade. It moves really fast. What moves that fast? Moore's law. So here's how I depict this as a graph. I like to track something I call the tiny application history. And the tiny application is something that I define as, it's silly to break this thing into pieces. You'd be embarrassed to tell your family and friends you did it, unless you're writing a PhD. So an example of a tiny app, if I had a 1 kilo element array I wanted to sort, doing that by going on to Amazon, getting Elastic MapReduce, renting 1,000 machines and getting the result back would be a silly way of solving a 1,000 element sort, right? My phone can do this about 100 times a second easily, okay? But if I had a petabyte, that would be the right way to do it. So this is not a question of is it right to distribute a problem, is it right to distribute a problem at a certain size? And if we look at it over time and use my memory of computers, which started about 1980, at 1980, 100 kilobytes was already tiny. By 1990, 10 megabytes was tiny. The 1 gigabyte heap is what we built the .com revolution on, or whatever we thought it was. And each one of those servers grew with Moore's law and with us, and we filled a little less than half of it. So today we can buy a 256 gigabyte server for less than $8,000, which is cheaper than any one of these. How big should the tiny app be? How big should the number that you'd be embarrassed to indicate to other people you break your applications to? It'd probably be 100 gig or so. But none of you were embarrassed to answer my question, and that's for a reason, because you're doing the right things today. You're doing what works. And the problem is that things stop working above the sizes you tend to go here, and the brave people that use 50 gigabytes know a lot about garbage collection. The memory wall, application memory wall, looks something like this. We stopped growing application sizes to fill memory, application instance sizes to fill memory about 10 years ago. And now we're at a gap that's pretty big. So what's behind this? Well, garbage collection. But it's not the efficiency of garbage collection, it's responsiveness. There's a practical level people just don't want to build unless they're doing batch apps. People don't like to stare at a screen for 3 minutes, and they get yelled at if they build applications that expect people to do that, so they don't build things that use memory that would cause a 3-minute pause. Most JVMs today will exhibit a multi-second pause at 2 to 6 gigabytes, which is why you guys stop there. And the root cause for the actual application memory wall is this link between scale and responsiveness. That's what needs to basically be fixed. Now, these are the things it's not about. It's not about efficiency. It's not about speed. Java's pretty damn fast. It's not about the minor GC events unless you're in the low latency trading world. And it's not about the frequency of the bad stuff. It's the fact that it happens at all. It's considered a crash if it's that bad. And people just don't like to build or ship crashed systems. So we don't. Now, what kind of problems does that are left in GC and how can we deal with them? Well, as I said, we need to get rid of this root cause, which is monolithic stop the world pauses. How do we do that? Well, we can apply many techniques, and let's look at some industry techniques. This is the most common technique used. We don't want to talk about the problem. We don't want to measure the problem. If we measure it, we'll find ways to not show it. Here's an example. Run the system for, how much is that? That's about 40 minutes. Nothing happened. It's good. If you run it a little longer, you get a couple blips. That's just measurement error, right? If you run it for a whole day, it looks like this, and that's what the real world is. So you face it, and this is your percentile behavior. Here's a different way of dealing with it. Let's rename the problem. Creative language. This is an actual quote from a guarantee from a JVM. I will guarantee a worst case of, say, 5 millisecond 99% of the time. Think about what this means. 1% of 1 hour is 36 seconds. I can pause for 36 seconds, but I've delivered what I promised. Another word is mostly. Right? You wanted a concurrent collector? Here it is. Mostly. Right? Fairly consistent behavior. I see that mentioned a lot. Okay, so you translate what you see said. Okay? Means the opposite. And typical pauses in the tens of milliseconds. That means sometimes you'll see terrible pauses that are much larger than 10 milliseconds. It says that right here. I was honest, right? And I assume all of you experienced these, and we all want to look at tuning the efficiency of things, but that's not the problem. So another way to deal with this is to measure stuff. I'm going to jump really quickly through a bunch of these. We built a tool called JHiccup that lets you measure things like this. It's kind of the incontinuity of execution. It shows you the, I don't know what your app did, but the JVM was not moving for that long at that point in time, and this is the percentiles of not moving over time. So whatever your app did, it's going to be worse than that. And you can add this as a Java agent or a wrapper to any Java application on any JVM and get this graph. Okay, so you're welcome to go look at that, and I'm going to just quickly skip through a set of slides because I've been going slowly than I planned. But how can we break through this thing? So we need to solve the core problems and eliminate the root cause. We need to unlink responsiveness from scale metrics, and these are a bunch of scale metrics in your terms or in the garbage collector's terms. And these are the hard things that are left in garbage collectors in order to achieve that. We know that because we solved them. So robust concurrent marking that is not dependent on your rate of execution. Doesn't fall off a cliff when you go fast. Concurrent compaction. Not stop the world and not incremental, because incremental doesn't seem to be cutting it. And this one people haven't hit yet, but we've hit it, so we built a generational concurrent collector for it. If you can't do young generation collection in size, you'll run into a big problem, because right now the only reason young generation pauses are small is because heaps are tiny. The young generation is a certain fraction of your heap. If you have a 100 gigabyte heap, you better be ready for 2 gigabyte promotions. And those will be as big as the entire big pause you have today for the entire JVM if you run them that size. So the only reason people aren't hitting that is because they're not running heaps that use half a server or a quarter of one. So this is a green highlighted way of saying what actually is needed for each of those problems. But fast forwarding, remember I told you I'm going to brag? So here it comes. Our C4 collector, and there's a full peer review paper on it. It stands for Continuously Concurrent Compacting Collector. So let's classify it. It has a concurrent guaranteed single pass marker. So no matter what your mutation rate, no matter what your transaction rate, this marker will complete in a single pass and find all the live objects and all the dead. It also has other things like concurrent ref processing and concurrent other things like finalizers. So other quirks are there. It has a concurrent compactor. It can move objects in memory, and it can lazily remap references without stopping you before it does that. It's a key thing. It has a concurrent compacting old generation, and it has a concurrent compacting new generation. Most importantly, it has zero fallback code to stop the world. The code simply does not exist. It's not rare. It's not only if I run into this problem. We just don't have this code. Okay? So I'm not going to get too much into the detail of how it works, but it basically uses the exact same algorithm for both young and old generations. It's a mark compact collector, so it's linear only to live set. And the only reason we use a generational collector is because it's 20 times as efficient as a non-generational one. We get the same pause behavior in both. We use a new type of read barrier called a loaded value barrier that in our latest generation of Zing optimizes down to a single x86 micro-op. That's the cost of putting it in the code. So it's fairly highly optimized as far as the dynamic cost of it. It has a very interesting self-healing property that makes it dynamically practical because it will only trigger once per object in every GC cycle instead of triggering hot in loops. The benefits of it look something like this. This is an academic graph, so it's a reverse logarithmic growing graph. Okay, we need to impress people with it. So good is up here. Latency drops as you grow up here. And what you're seeing is the C4 collector in purple compared to the parallel GC and the CMS collector plotted on worst case behavior on a benchmark. This green line is the C4 collector with generational turned off. It reaches similar levels of goodness, but it takes a lot more memory and is less efficient in getting there. What you want is a collector, what you want is a flat plateau like this. The part before this plateau is when we just don't have enough memory to collect as fast as you're allocating. This thing was allocating 1.2 gigabytes a second, and it has a 2.5 gigabyte live set, so trying to fit it in a 3 gigabyte heap is kind of like that 1 byte in a gigabyte problem I was talking about before. But once you give it enough memory so it could close its cycle from a throughput perspective, all this does is change efficiency but not response time. Okay? You're not seeing the efficiency on this graph, you're just seeing the response time. So that's a response time behavior way. That's the difference between generational and not. Zing is the thing that wraps this, and I said I'll talk about it, but I'm not going to talk too much. We have a booth back there. You could get information about it, but I like to talk about sustainable throughput, not just latency. And throughput and sustainable throughput are two very different things. Sustainable throughput is how fast can you go without the bad things happening, and throughput is how fast can you go and you don't care if bad things happen. Let me depict that for you. Okay. That's not sustainable speed, it's speed. You go too fast, this happens, right? And that's why we like to measure how fast can you go while meeting SLAs, rather than just how fast can I go, and I don't want to measure response time at all. So this is a depiction of that. This is actually a little aged now, but it's a live ray portal running on JBoss on a machine with 96 gigabytes, and we ran to, this is the SLA, once 90% better in 1 second, 99% better in 5 seconds, everything better than 10 seconds. Most of our customers would say that's not good enough. But let's be relaxed here. And we wanted to see how fast or how many concurrent users of load can you load up this thing on the workload before you crack. And this is close to cracking. So we got about 45 concurrent users in a 3 gigabyte heap. Zing did this. Flat, but this is 800 concurrent users. Same machine, same workload. How did we do this? We cheated. How did we cheat? We used half the computer. 50 gigabytes of heap instead of 3. We've got room for all the users. We're sustaining 3.2 gigabytes per second of allocation, and we've got room to grow. That's throughput, but sustainable throughput. You can get CMS to run that fast. You just need to deal with the multi-second hiccups that happen in the middle. Remember I told you about hiccup? Well, this is a quote from Charles Nutter about why we built it. He's right. It's really to show you how good our stuff is, but it lets you see it with any JVM. And it highlights things like this. Zing is on the right, Oracle Hotspot on the left. This is a 1 gigabyte data set in an 8 gigabyte heap. See how much prettier Zing is? Well, maybe not because the numbers are small, so I'll highlight them. That's a 14-second pause. That's a 20 millisecond pause. If I scale them, they look like this. Okay, that's our before-after why you want Zing picture. The other reason you might want Zing is you might be doing this a lot. Remember what I told you I won't teach you how to do? And you might find that this is right, or that is right, or this is Wednesday and that's Thursday. Tuning Zing goes like this. Give us a lot of empty memory, and we'll do the rest, right? And empty memory is cheap. And last is, human response time apps, which a lot of you are dealing with, or messaging apps are one thing, but low latency is an interesting world we're doing very well in because really there's no competition there. Everybody else's young gen collector is a stop-the-world collector. With Zing, you can pretty much get to less than 10 millisecond worst case without much effort in the low latency space. You can get to 2 to 3 milliseconds worst case with a little bit of tuning, a few days, and we have some people who have gone below a millisecond absolute worst case measured on their system. This is a system. Now this is a low latency system, so these guys have tuned it so for 3 days it never sees an old gen, and then they restart it every night so they never see an old gen. So this is purely new gen, and they've tuned the new gen so it's pretty good. See, the worst case on it is like 20-some milliseconds. Unfortunately, these guys are doing 100 microsecond trading, and 20 millisecond blip in that is a problem. This is a percentile chart of what happens. At about 99%, the response time goes up. This is Zing compared to that with a similar technique to before. Again, scaled graphs, it actually looks like this. So that's it as far as the pictures and the before-afters. One last thing before we go. We've got an initiative that we announced a few months ago to support open source. Basically, access to Zing is free for developers and testers of open source projects. And basically, it's running on these operating systems, plain vanilla, unmodified Linuxes if you want them. And that's it. Thank you.